Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when values of transmission line parameters and load details are given. Using nominal pi method, we have to determine the efficiency of transmission and percentage voltage regulation of a three-phase transmission line 160 km long delivering 15 megavolt ampere load at 110 kilovolts 50 Hz 0.9 lagging power factor. The line has inductance of 1.356 millihenry per kilometer per phase, capacitance of 0.0085 microfarad per kilometer per phase, and resistance 40 ohm. Let us now write down the given data. Load SL equals to 15 megavolt ampere, that is equal to 15 into 10 to the power 6 volt ampere. Line to line receiving end voltage via line equals to 110 kilovolts, that is equal to 110 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 110 into 10 to the power 3 divided by root 3, that gives us 63,508.53 volt. Given load power factor cos phi L equals to 0.9 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.9, that is equal to 25.842 degree. Expression for load SL equals to root 3 times via line into IL. Therefore, load current IL equals to SL divided by root 3 times via line. Using values we get 15 into 10 to the power 6 divided by root 3 into 110 into 10 to the power 3. That gives us 78.73 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 78.73 ampere at an angle minus 25.842 degree. This may be written in Cartesian form as 70.857 minus J times 34.3177 ampere. Now we shall calculate power delivered to the load. PL equals to SL into cos phi L. Using values we get 15 into 0.9, that is equal to 13.5 megawatt. Given length of the transmission line D equals to 160 kilometers. Resistance per phase R equals to 40 ohm. Inductance per kilometer per phase L1 equals to 1.356 millihenry and capacitance per kilometer per phase C1 equals to 0.0085 microfarad. Let us now calculate inductance per phase L equals to L1 into D. Using values we get 1.356 into 160, that gives us 216.96 millihenry or 0.21696 Henry, and capacitance per phase C equals to C1 into D. Using values we get 0.0085 into 160, that gives us 1.36 microfarad or 1.36 into 10 to the power minus 6 farad. Now we shall calculate inductive reactance per phase. XL equals to 2 pi F into L. Given supply frequency F equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.21696, that gives us 68.16 ohm. Capacitive susceptance per phase BC equals to 2 pi F into C. Using values we get 2 pi into 50 into 1.36 into 10 to the power minus 6, that gives us 427.2566 into 10 to the power minus 6 mho. Series impedance per phase of the transmission line Z equals to R plus JXL, that is equal to 40 plus J times 68.16 ohm. This may be written in polar form as 79 ohm at an angle 59.5933 degree. We have obtained series impedance per phase of the transmission line Z equals to 79 ohm at an angle 59.5933 degree. Capacitive susceptance per phase BC equals to 427.2566 into 10 to the power minus 6 mho. Let us now calculate capacitor charging current at the receiving end. ICR equals to VR into half of J times VC. Taking receiving end voltage per phase as reference, we can write VR equals to 63,508.53 volt at an angle 0 degree. Therefore, ICR equals to 63,508.53 at an angle 0 degree into half of 427.2566 into 10 to the power minus 6 at an angle 90 degree. That gives us 13.5672 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 13.5672 ampere. Let us now calculate current flowing through the series impedance. I equals to IL plus ICR. We have obtained load current IL equals to 70.857 minus J times 34.3177 ampere. Using values we get I equals to 70.857 minus J times 20.7505 ampere. This may be written in polar form as 73.8329 ampere at an angle minus 16.3227 degree. Now we shall determine sending end voltage per phase. Vs equals to VR plus I into Z. Using values we get 63,508.53 at an angle 0 degree plus 73.8329 at an angle minus 16.3227 degree into 79 at an angle 59.5933 degree. That gives us 67,755.534 plus J times 3,998.0619 volt. This may be written in polar form as 67,873.389 volt at an angle 3.377 degree. Now we shall compute Sending end capacitor charging current ICS equals to Vs into half of J times Vc. Using values we get 67,873.389 at an angle 3.337 degree into half of 427.2566 into 10 to the power minus 6 at an angle 90 degree. That gives us 14.5 ampere at an angle 93.377 degree. This may be written in Cartesian form as minus 0.8541 plus J times 14.4748 ampere. Let us now calculate sending end current. Is equals to ICS plus I. Using values we get 70.0029 minus J times 6.2757 ampere. This may be written in polar form as 70.2836 ampere at an angle minus 5.123 degree. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 67,873.389 volt at an angle 3.377 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 70.2836 ampere at an angle minus 5.123 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 67,873.389, which is approximately equal to 117.56 into 10 to the power 3 volts or 117.56 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 3.377 degree plus 5.123 degree, that is equal to 8.5 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 8.5 degree, that is equal to 0.989 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 67,873.389 into 70.2836 into 0.989, which is approximately equal to 14.15 into 10 to the power 6 watts or 14.15 megawatt. Let us now determine efficiency of transmission. Eta T equals to PL divided by PS. We have obtained power delivered to the load PL equals to 13.5 megawatt. Therefore, eta T equals to 13.5 divided by 14.15, that gives us 0.954 per unit or 95.4%. Now we shall remove the load from the receiving end and calculate capacitor charging current at the receiving end. ICRO equals to Vs divided by Z minus 2 times JXC. We have obtained sending end voltage per phase Vs equals to 67,873.389 volt at an angle 3.377 degree. Per phase series impedance of the transmission line Z equals to 40 plus J times 68.16 ohm, and capacitive susceptance per phase DC equals to 427.2566 into 10 to the power minus 6 mho. Let us now calculate capacitive reactance per phase. XC equals to 1 upon DC, that is equal to 1 upon 427.2566 into 10 to the power minus 6, that gives us 2340.5 ohm. Now we shall compute Z minus 2 times JXC. Using values we get 40 minus J times 4612.84 ohm. This may be written in polar form as 4613 ohm at an angle minus 89.503 degree. Using values we get ICRO equals to 67,873.389 at an angle 3.377 degree divided by 4613 at an angle minus 89.503 degree. That gives us 14.7135 ampere at an angle 92.88 degree. We have obtained capacitive reactance per phase Xc equals to 2340.5 ohm and capacitor charging current at the receiving end on no load ICRO equals to 14.7135 ampere at an angle 92.88 degree. Let us now determine receiving end voltage per phase on no load. VRO equals to ICRO into minus of 2 times JXC. Using values we get 14.7135 at an angle 92.88 degree into 4681 at an angle minus 90 degree, that gives us 68,873.894 volt at an angle 2.88 degree. Now we shall compute voltage regulation, that is equal to VRO minus VR divided by VR. We have obtained receiving end voltage per phase on load. VR equals to 63,508.53 volt. Therefore, voltage regulation equals to 68,873.894 minus 63,508.53 divided by 63,508.53. That gives us 0.0845 per unit or 8.45%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to compute voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.